Nice. All right. Thanks everyone for coming. So today we've got Juan, who's a postdoc with Adam Hansen in Warwick, and he's going to be talking to us about some recent work on sort of variations on the EM algorithm. So yeah, Juan, please get going.
Okay. Thanks, Sam. Thanks for having me. And hi, everyone. As Sam said, for those of you that don't know me, I'm Juan, postdoc with Adam over at Warwick. And today I'm going to talk about some algorithms that we've been working on for a bit shy of a year and more intensively over the last half a year. In short, they do the same thing that EM does, but they apply to settings that EM doesn't. We put up a preprint on arXiv around a month or so ago. So if you like any more information about anything that I say today, that's the place to go look. That said, if you have any questions at any point, please just stop me and ask. Okay, so before we get started properly, I should give a sort of disclaimer. We played it pretty fast and loose with all the rigor stuff. So we literally, in the preprint, we have somewhere we're describing as setting notations, a rigor and lack thereof, right? So please don't expect too much from me on that department today. When I say that we prove this or that, take it with a grain of salt. It's up to, integrability assumptions and so on. If you want, there's this blurb in the paper explaining all the places that we were not rigorous. There's a flip side to this though, because Adam and I have set the bar so low in this respect. There's loads of room for people to do nice theory here. So if that might be anyone's cup of tea, please do let me know. Okay, so with the legal stuff out of the way, let's start properly and maybe just with the kind of high level ideas that motivated all of this work. And they're pretty simple. It's just that some problems in sampling and computational statistics are optimization problems, or you can rephrase them as optimization problems if you take a little bit of care. And sometimes, not always, but sometimes you can do well by treating them as such. And by this, I mean by trying to solve them using an optimization algorithm or something like. In particular, once you make this connection, you kind of gain access to the entire arsenal of like tools, methods, theory that has been developed for optimization. And sometimes that can be pretty helpful and especially guide you into trying to do something reasonable. These are not revolutionary new ideas. I'm not the only person in the world thinking along these lines. I'm probably not even the only person in this call, at least at times. But I do think that sometimes we exploit them a little bit less than we can. And today I'm going to try to persuade you of their usefulness by basically going through an example, taking one of these problems and taking one of these approaches to try to solve it and hopefully getting somewhere else. So the problem I'm going to deal with is called empirical Bayes. And in it, we've been given some data, Y, and of like observations in the real world. And we want to use it to infer some unobserved or latent variables X. And in order to do that, we're going to try to use a probabilistic model. And by this, I just mean a joint probability distribution over the data and the latent variables, and one that is parameterized by some parameters. And throughout, I'm going to make my life simple, and I'm going to assume that both the latent variables and the parameters take values in Euclidean space. So here's this kind of silly toy example that I like to test algorithms on, just to make sure we're all on the same page. And in it, the data consists of capital D many real valued observations that we've made. And each of these is kind of like a noisy measurement of a corresponding latent variable, which we'd like to infer. And I'm going to use a very simple model. The model says, well, each observation is the corresponding latent variable plus some IID 0,1 Gaussian noise. And all the latent variables are drawn from the same distribution independently of each other, and the distribution is a scalar Gaussian with mean theta and unit variance. So the model altogether looks like this, or its density. I'm going to conflate densities and measures throughout the whole time, so apologies about that. Okay, so we'd like to use this and use the y's to try to figure out what the x's might be. Now, if you're a frequentist, you would probably do something like maximize this quantity over both theta and x, and then extract the x's that you got from that optimal pair and use those as a point estimate of what the latent variables might be. If you're a Bayesian, you say like, no, that's rubbish. You're not quantifying the uncertainty in your estimates. What you should do is assign a prior over the parameters. So you turn the whole thing into a distribution over theta, x, and y. Compute the corresponding posterior over theta and x given y. integrate out the parameters, and that will give you a distribution over the latent variables, and that you can use to reason about in a statistical way about what values they might take. So I'm going to work somewhere in between these two by following what's known as the empirical based paradigm. And in it, what you do is you first look for a point estimate of the parameters that explains the data well, that's consistent with what we saw. And once you have this point estimate, you use it to draw inferences on the latent variables with quantifying the uncertainty in your guesses. What we really actually do is we look for thetas that maximize the marginal likelihood or the probability of seeing what we saw of the y's, according to our model. And once you have these, you compute the corresponding posterior distribution over only the latent variables. And you use that to, try to infer what they might be in a statistical way. Now, the issue here is the same as always. This is an integral over the latent space. Latent space is often high dimensional, so we can't compute it exactly. We don't have closed forms, and it's hard to approximate it numerically, so we have to work around that. Now, something that I personally like about empirical base is that it doesn't force you to elicit a prior on the parameters, which for some models out there can be a pretty unnatural exercise. So models in which the parameters might not have any sort of physical interpretation. There's no reasonable information you can try to encode in your prior, and even using uninformative priors can prove difficult technically. And in some areas, this is more the norm than the exception, things like statistical machine learning and that sort of stuff. Okay, so probably the best known algorithm for carrying out this program, for finding these optimal thetas and the corresponding posterior, is the EM algorithm, or expectation maximization algorithm. And it's pretty simple. It just says that you start from some guess of what the parameters might be, and a guess of what the corresponding posterior might be, and then you alternate these two steps, the E step and the M step. In the E step, you update the Q's by setting them to be the posterior corresponding to your current parameter estimates. And in the M step, you update the parameters by maximizing the subjective here over all possible parameter values. Right? And this objective is an integral with respect to the posterior you just worked out. And the integrand is the log of the model density. Now, EM is a very classical algorithm. It's been kind of like studied to death. And we know that under quite general conditions, the parameter estimates converge to a stationary point of the marginal likelihood, and the Q's converge to the corresponding posterior in an appropriate way. And here you might say, hold on, I thought we were talking about maxima of the marginal likelihood, not stationary points. And I would say, well, in that case, you would want to try to consider the convexity properties of this guy here, or the base construction of the algorithm, and so on. In general, in non-convex settings, the best you're going to be able to guarantee are stationary points. Now, for me, the main issue with EM is that you can't actually do the E and M steps for many models out there, most models, I would say. In particular, in the E step, we have to be computing posterior distributions, which means evaluating the normalizing constant, which is that integral over latent space that was causing us issues in the first place. And in the M step, well, you still need to compute integrals over the latent space, and on top of that, optimize over them, which proves difficult in many cases for the same sort of reasons. So what do people do in these cases where they can't do these steps exactly? Well, they just do them approximately and then alternate between them as before. So in the E step, it's quite common to just use Monte Carlo. So people might do something like run an MCMC chain targeting the posterior for the current parameter values, or a particle smoother if you're in a state size model type context. And then that gives them this like finite sample approximation to this guy. They plug it in here, which gives them a surrogate objective they can actually evaluate. And then they optimize that using their favorite like numerical optimization routine. And often they will do things very simple. They might not do a full optimization run. They'll do like a single gradient step or a single Newton step. And then they keep alternating between these two until they get some sort of convergence coming out. Now, there's this interpretation of EM that I really like. I think it makes it quite intuitive why it often works. It goes as follows. It says that EM is a well-known optimization algorithm applied to a particular objective called the negative free energy. Right? And this objective looks like this. It's a functional that takes in parameter values and probability distributions over the latent space and spits back out real numbers. Now, you might wonder what this has to do anything with our problem, and the connection is here, right? And this stems, well, actually, this whole perspective predates this paper here, but I think this paper has a really nice and accessible presentation of it. And in particular, it turns out that the marginal likelihood has a global maximum at some particular thetas, if and only if the free energy has a global maximum at those thetas together with the corresponding posterior distribution over the latent space. So if we could only just optimize this thing over all thetas and q's, we would recover a maximum of the marginal likelihood, and on top we would get the posterior over the latent space, which is what we need to draw inference on the latent parameters. Now, as for EM itself, it turns out that it's what people in optimization call coordinate ascent or coordinate maximization applied to this objective. And the connection here is this other one line that you can argue in about 2 lines. And it just says that if you fix theta and you maximize the free energy over the q's for the fixed theta, the q that maximizes it is the corresponding posterior. So this E step that tells you update the q's by setting them to be the posterior corresponding to your current parameter values is the same as just update the q's by maximizing f over q, keeping the thetas fixed at your current parameter values. And as for the M step, well, if you squint at this thing here and at that thing there for around 10 seconds, you'll realize that maximizing one of these over theta is the same as maximizing the other one. So we can also write the M step as one of these coordinate maximization steps. This time we fix the q's to whatever came out of the E step, and we maximize over theta. So we have this coordinate maximization. We fix one argument, maximize over the other, then fix the other, and maximize over the first. And I like this kind of interpretation because it lets you draw cartoons that give you kind of a little bit of an intuitive feel of why EM might work. So here's one such cartoon. The free energy is coming at you from the slides. So yellow is high and blue, purple is low. And we have our Q axis, our theta axis. And EM says, well, you just start somewhere. And you, oh, yeah, sorry. Here I've also plotted these 2 lines, right? This is the line of, for each fixed theta value, what's the Q that maximizes F, and vice versa. This is for each fixed Q value, what's the theta that maximizes F. So EM, you start somewhere and you maximize over Q. So you move vertically until you hit the corresponding line. And then you freeze Q, you maximize over theta, and you move horizontally until you hit the other line. And you keep bouncing up and down until moving towards naught. So this is all well and good, but it doesn't really do much to solve the problem I said before about the E and M steps being intractable for many models, right? And this is exactly the same issue that coordinate ascent has. It's why it's a bit more niche of a method than like gradient ascent or Newton's or whatever. You often can't do the coordinate maximizations exactly for most objectives out there. So what do people in optimization do in these settings? Do they try to do these steps approximately and alternate as before? No, they generally just apply a different optimization algorithm to their objective. I should say this is a little bit of a shame because coordinate ascent, when you can do the steps exactly, often does really well. It often outperforms first order methods, not always, but often. And for some problems out there, it's considered the state of the art, things like Lasso, where coordinate ascent and first order methods have a similar complexity. However, if you look at this literature and you look at it in the cases in which you can't do those steps exactly, whether that this is still the case, you still outperform other methods, it's really unclear. And honestly, I can't find much evidence in favor of this. Normally, I only see people doing approximate coordinate ascent when the problem is in such a way that they can't do something else. So maybe it's so big that they can't store full gradients in memory. They have to break them up into chunks and then do things coordinate wise. And even just kind of intuitively, if you're doing these steps only partially, right, you can see that the convergence slows a lot, right? You miss out on the nice things about coordinate ascent, which are these kind of big moves early on. Okay, so that begs the question, can we do something similar for the free energy? Can we apply a different optimization algorithm to it? In particular, maybe we should drop this coordinate-wise pretense. Now, this is also not a revolutionary new idea. Even in that paper by Neil and Hinton from around 20 odd years ago, they mention in passing that the perspective they expound there would justify algorithms in which you would maximize both Q and theta simultaneously. You would update those together. And if you look at the variational inference literature, this idea is kind of all over the place, right? And especially in the appendices of many of these papers. So there they will restrict the set of all possible distributions of a latent space, and will restrict it to a tractable subset of it. And particularly, it'll be a subset of distributions parameterized by some parameters that they call variational parameters. And then they'll take this form here, plug that into the free energy, and optimize it over the variational parameters lambda and the model parameters theta. And if you look at how they're doing those optimizations, they're generally not optimizing over lambda and then optimizing over theta. In many cases, they're running an optimization algorithm over both lambda and theta together. Now, if you look outside of this literature, if you don't want to deal with trying to pick a parametric family and the possible headaches that can bring with you, right? And you just say, okay, what about optimizing F over the space we care about? Then Adam and I had struggled a lot trying to find much about this. Many people following up on this suggestion of Neil and Hinton. And, the E.M. Dempster paper is cited around 70,000 times by now. I can tell you that I have not read all of those references, and we easily can miss something. We did miss stuff. So even here, Sam had a blog post basically giving the same sort of idea from around, I don't know, 10 months ago, something like that. So yeah. But incidentally, if anyone else knows of anywhere where these kinds of ideas are there, please do let me know. Paper preprint, blog posts, Insta story, whatever. I'd be interested in hearing. Okay, so back to our setting. We had this question: can we optimize the free energy over the space we care about using a different optimization algorithm than EM or coordinate ascent? In particular, what about just gradient ascent, the first algorithm that you'll encounter if you just open an undergrad textbook on optimization. And that eventually led us to this thing that we call particle gradient ascent, for the lack of a better name, that seemed to kind of work. And let's see. So let's start easy. Gradient ascent for maximizing a function on our end, a functional on our end. It's a very simple algorithm. It just says you start somewhere and you take steps in the direction of the gradient evaluated at where you started. So you move perpendicular to the contour line where you started, and then you update the gradient direction, you move again perpendicular with respect to the contour line, and you keep doing this until you converge or until the gradient vanishes. So in order to try to look for an analog of this, we're actually not going to really examine the gradient ascent algorithm. We're going to examine its continuous time counterpart. So if you were to take these steps ever smaller, right, and infinitesimally small, you get what's known as the gradient flow. It's the set of ODEs here, and it just says you move smoothly through space, constantly moving perpendicular to whatever contour line you're on right now. And people usually care about this thing here because it's very easy to analyze mathematically, to argue about its convergence, to at least stationary points, reason about its speed of convergence and this sort of thing. So people like studying this thing because it's easier to study gradient ascent, which is the Euler discretization. So in our case, what we're going to do is to look for an analog of gradient ascent. We're going to turn things around. We're going to look for an analog of the gradient flow that applies to the free energy, and then discretize it until we get an algorithm that we can actually run on my computer. So the gradient flow will look very similar. It's just an ODE, and it tells you we keep updating the thetas and the q's by just following the direction of the gradient of the free energy, or the negative free energy. Sorry, I'm going to keep saying free energy when I mean negative free energy. You're going to have to bear with me on that. Okay, so at this point, you might say, well, what do you mean by the gradient of the free energy? On Euclidean spaces, we all agree what gradients are. But here, this is a functional defined over parameter space crossed with a measure space. Now, it turns out that we figured out how to answer this question over the last 20 years or so. And what you need, or at least the bare minimum you need on a space in order to be defining gradients on it, is a metric. And how do I, so just kind of, this is not exactly the same, but just intuitively, here we want to move in the direction of maximum ascent for the free energy. So out of wherever we are right now, out of all the small steps we could take, we want to take the one that increases the value of F the most. In order to be able to reason about this, you need to define what you mean by a small step, right? To compare points the same sort of distance away from you. And that's where the metric comes in. Now, once you choose a metric, and assuming all the technicalities along the way work out, there's this kind of standard way of arriving to a notion of gradient. And the metric we used is very simple, and we picked it for practical reasons because it gave us a gradient flow that was easy to approximate and run an approximation in practice, not for theoretical ones. I really don't think this is the best choice of metric you could choose here. If anyone's interested, ask me and I can elaborate on what I think is good. But the one we chose is just the sum of the Euclidean metric on the parameter space and the Wasserstein 2 metric on the space of probability distributions of the latent variable. And once you make this choice, the notion of gradient that you arrive is given by this. It's given by this tuple in which you have a theta component that will tell you how to move, how to update the thetas, and a q component that will tell you how to update the q. And the theta component, it's simple. It just reads, well, you take gradients of the log of the density of your model with respect to theta. You evaluate them at whatever theta you are right now, and you integrate that with respect to the whatever q you are right now. And as for the q component, well, if you look at it, it reads like this thing here, which looks like the right-hand side of a Fokker-Planck equation. And I mean, you can also just view this as a signed density that will tell you how to move your entire density. In particular, if you integrate this over x, you get 0. Right? So you get this thing that it moves you in directions where you preserve the mass of the probability distribution. Okay, so we have these expressions, and then to define the gradient flow, we just plug them in for the gradient, and you get these things here, right? These sort of ODEs. Now, at this point, it kind of helps just to run some sanity checks. We chose a notion of gradient for the free energy. What are the stationary points according to this notion? What thetas and q's make the gradient vanish? And it's pretty easy to check, just a few lines of calculus, technicalities aside, that theta and q make the gradient vanish if and only if theta is a stationary point of the marginal likelihood and q is the corresponding posterior. So that's good because these are exactly the sort of points that we're interested in. And if you work a little bit harder, you can start showing convergence of this guy here to these types of points as t tends to infinity. We did this in a very simple case. We did this under strong concavity assumptions on the log of the density of the model, in which case you get exponential convergence, and using kind of standard arguments extended to this slightly unconventional setting. But I don't want to really dwell on this too much because I don't think these assumptions are important at all, at least to argue convergence. I think you can argue it very generally by using an extension of Lassalle's invariant principle. But we didn't go the whole way. We didn't actually do this, but I can elaborate with this if anyone's interested. Okay, so we have good evidence to believe that this gradient flow takes us to the kind of points that we want to go, the thetas and q's that we're interested in. So if we could just run this in practice, that'd be great. But of course, you can't. It's intractable for a bunch of reasons. First of all, we have a continuous time axis, so we can't just run that on a computer. We need to, we need a recursion. We need to discretize somehow. On top of that, we still have an integral over the latent space, which was the thing that was causing us issues from the very beginning. And on top of that, I've managed to basically add a PDE whose domain is the latent space, which is high dimensional, is not the type of thing that you can just solve. So I'm going to deal with these one at a time, some approximating and others not, until I get something that I can actually run on my computer. So first up is the PDE. And the trick we used here was just noting that this thing together, it's basically a McKean-Vlasov-Fokker-Planck equation that is satisfied by the law of this SDE here. So what I mean by this, well, this here is the same as that, just rewritten in SDE notation. And then if you look at this thing here, this looks like the Fokker-Planck equation of the Langevin diffusion targeting this posterior here, or its unnormalized version. The only difference really is that this is changing over time. So our posteriors are moving over time. And you get that by having this drift term that changes over time. So in short, if Qt is the law of xt and xt satisfies this equation here, Qt will satisfy that equation. Okay, so next up is the integral over the latent space. And well, what do you do when you can compute an integral over a space? Oh, at least what do I do? Just use Monte Carlo. So I'm going to generate capital N particles, each of which have the same law and that are independent of each other. And then the law of large numbers tells me that if I've generated enough of these particles, then their empirical distribution is a good approximation to their individual laws. And then I can plug this into the integral to get this kind of like stochastic gradient approximation to this integral that I need here. And to generate these particles, I really don't just take this equation, copy paste it n times, and drive each of these by an independent Brownian motion. And then because the thetas here, well, they follow this deterministic equation, they don't correlate these particles, at least at this stage. So all of these particles are independent of each other. Okay, so that just leaves us with the continuous time axis. And we did the simplest thing we could think of, was just throw Euler-Maruyama at it, and then we get these recursions that you can actually run on your computer. And actually, if you squint at these recursions, you start seeing things you recognize. So this thing here looks like stochastic gradients, more or less, for the thetas for a particular object. And this here, this is, well, we have capital N kind of unadjusted Langevin chains that are following this posterior that is moving over time, that changes every time we update theta. So, and then this is what we call particle gradients, because we didn't have a better name for it, so PGA. And basically we just run these recursions for enough time, capital K amount of steps. Then we use the parameter estimates we have at the end of that run as an approximation of a stationary point of the marginal likelihood, and the empirical distribution of the particle cloud at the end of the run as an approximation to the corresponding posterior. Or you can average these over time after discarding some steps from burning, the same sort of thing as an NCNC. So we have this analogy between PGA and kind of gradient descent, or I should say stochastic gradient descent, because we've replaced this integral with an empirical average. So we can start to make some guesses on how PGA might behave from what we know about how SGA behaves. And I should say SGA with a constant step size, because we're not doing anything fancy. We're doing the simplest thing we can. So in particular, is the step size h that we use to discretize time is too large, then PGA will be unstable. Otherwise, you'll have a transient phase, after which the parameter estimates will hover around the stationary point of the marginal likelihood, and the empirical distribution of the particle cloud will hover around the corresponding posterior distribution. And by hover, I mean hover in a way that if you average over time, the parameter estimates actually converge to the stationary point of the marginal likelihood, and the posterior approximations converge to the corresponding posterior. And then lastly, well, the smaller you pick h, the longer you'll have a transient phase, because it takes you longer to burn through it, but the lower estimator variance you'll have in the stationary phase, because you'll be hovering around this optimum point and taking very small steps around. Now, when we tried this in practice, this is what we saw up to one caveat. And the caveat is that the time averages, they don't actually converge to an optimum of f, or a stationary point of f, I should say, but instead to a point in the vicinity of an optimum. And this is really not surprising, because if you look at this thing, we're here reliant on Euler chains, and Euler chains are biased, right? So it's not strange that we also get a bias here, right? And one that does not go away asymptotic. However, you can mitigate this bias by just growing the particle number and decreasing the step size. So whenever we did this, we could get the bias to go to 0. And maybe this is not too surprising, because if you use large particle numbers and small step size, then hopefully you're doing a pretty close approximation to the gradient flow. And we do know that the gradient flow goes to the type of points we want it to go. Okay, so maybe I can just show you guys some pictures of what this actually looks like. So here's for that starting example. And here I'm plotting the parameter estimates as they over the number of iterants. Now, in this example, things are very simple. So I can actually compute what the optimal parameters are. So it's this dotted line over there. And also I can implement the EM steps. So I can actually compare with EM. And just to give you guys an idea, I was using 100 latent variables here. So the latent space is 100 dimensional. I was just using 10 particles when I was running PGA. And PGA looks like this. It's this blue line. You have this kind of transient. And once you reach around the optimum, then it starts to hover around it in a way that if I average over time, like I'm doing starting from here, you get something very close to it. When you compare with EM, however, you see that EM goes way faster, right? EM converges in around 5 steps, while it took PGA here to converge around 150 steps. However, it's not difficult to do some not kind of small tweaks to PGA to get it to converge a lot quicker in a way that is kind of comparable with EM. In particular, PGA, the way I've written it there, it's kind of a little bit ill-conditioned, because the theta gradients can be a lot bigger than the x gradients, so you probably want to be a little bit more careful. So you have this kind of obvious reason why it goes slow, but the good news is that it's obvious, so it's also kind of obvious how to try to mitigate. Okay, so here's a for more complicated example, in which you can't actually run EM because you can't do the steps. And here we need, for these types of examples, we need something else to benchmark against. And we use this SOL algorithm that Valentin, I don't know if he's here, but Valentin and company proposed a few years ago, and it was published last year. And it's quite similar to what we were doing. It's one of these approximations to EM, in which you approximate the E and you approximate the M step. And for the E step, what these guys were doing is they were running a single Euler chain in serial, targeting the current posterior, right? And then using, the empirical distribution of the states visited by the chain as an approximation to the posterior. And they were doing this one trick that actually made a big difference in practice, is that they would start each chain where the previous one left off. And this is kind of crucial to these things working well. And I actually think this is a quite nice algorithm. They were being pretty smart about what they did, and they were motivated by trying to overcome scalability issues in previous versions of these approximations to EM. That kind of has been a thing. In particular, for example, they avoided accept reject steps on purpose because they can be a bit finicky in high dimensions. Now, as for the M step, they were doing basically almost the same that we were doing. They just changed their posterior approximation to be the empirical distribution of the states visited by the Euler chain, instead of this particle cloud, which are Euler chains running parallel for a single step, like we were doing. And then we tested it in a bunch of examples. Here's the largest one we did, which is maybe not small for computational stats standards, but quite small for machine learning ones. And we were partly motivated by, we wanted to have all our examples run on Colab notebooks, which, by the way, on the preprint is Colab notebooks. So if you want to play with this without actually having to write a line of code yourself, You can just go there and click. So the example was MNIST classification, or a scaled down version of it. We were using a 2-layer basic neural net with isotropic priors on the network weights for whoever of you guys this makes sense to. It's not that important, the details. I guess here are the main points. The latent variables were the network weights, and there was around 30,000 of these. So we had a 30,000 dimensional latent space. And the parameters were just the prior variances. And there was one of these per layer in the network, so there was just 2. And then what we would do is basically use this to get an approximation of the posterior distribution over the network weights, trained on some training data, and then use that approximation of the posterior to predict on a set of held out test data. And then the lower prediction error is used kind of as a surrogate for quality of your posterior approximation. So this is what we found when we run PGA, its variance, and also SOL. And here's the test error, and here's the amount of time it took to run for different particle numbers. So if we use a single particle, all algorithms did pretty similarly. Actually, SOL did a little bit better on these runs, but nothing too different. And the time it took to run is more or less the same for all of them. And it's not surprising, because for a single particle, they all look very similar, these algorithms. But as you increase the number of particles, then things got a little bit more interesting. The first thing that kind of caught us off guard is that SOL didn't really seem to improve its predictive performance at all, at least for not huge numbers of particles. While the other ones, you did see a steady kind of a decrease in the error, which is more or less what you'd expect. And the other sort of salient difference was that with higher particle numbers, our PGA and its variance ran a lot faster than SOL. And that gap grew as you added more and more particles. And that one is really not very mysterious at all. When we update, in each update, we update, for example, 100 particles with a single Euler step. So that means computing gradients and adding Gaussian noise to them. And you can just vectorize all those computations, which mitigates the larger particle. And that's pretty easy to do on things like JAX and TensorFlow and stuff that's available these days. On the other hand, when you're running SOL, well, you need to run this Euler chain in serial, so you can't really take advantage of those things. And as for the test error, the explanation we have so far, it just comes from plotting the posterior approximations. Right? Here's a single coordinate and a particular, some coordinates would look like these, other would look a little bit broader for SOL. But what you would see is that the SOL approximations would be pretty peaked compared with the other ones. And if you think about it, it's not that crazy, because things are relatively high dimensional, so you have to take small step sizes. And in SOL, you take one particle and you move it forward by a small gradient step and a small amount of noise. Right? So all those particles are pretty correlated, one with the other. And if only after 100 steps or so on, they really don't move much. So the posterior approximation you get looks an awful lot like the one you did with a single particle. Right? And that kind of explains the sort of no noticeable difference in prediction error, because the posterior approximations don't change much. On the other hand, in our case, well, we're running the 100 chains in parallel, say 100, and they're each driven by different noise, so they're not really correlated. The only correlations come from the parameter updates, but that's kind of like a mean field sort of thing. So the correlations are pretty weak among the particles, and you get them spreading out a lot more. In particular, you don't get them all stuck on the same mode of the posterior. Okay, I think I've probably tortured you guys enough with this stuff, so I'm just going to wrap it up by, well, first describing the things that we like about PGA and its tweaks, and the things we like less. So let's start with the ones that we do like. You can use these algorithms in fairly broad classes of models, ones with Euclidean parameter and latent spaces, and with differentiable densities. They're pretty straightforward to implement. You just need to evaluate gradients and add noise, which is not too taxing normally. And also to tune. I don't think they're very difficult. In particular, you choose a large step size, things are unstable. You choose too small, you see it moving very slowly and very smoothly. and you want to aim for somewhere in the middle of that, and that seems to more or less work. Something I really like about these things is that you kind of recycle posterior approximations. So in particular, in things like SOL and these other algorithms in which the E step is approximated by running MCMC, they might do like run a whole long chain to obtain a posterior approximation. Then they use that to compute one gradient for the thetas and update the thetas. And then they just start from scratch, right? And you might have spent 1 million samples there, and that effort, you don't really use it much. Actually, Valentine, they were actually using that because they were starting the new chain where the previous one left off. And that kind of helps you track the center of mass of your posterior. In particular, the parameter steps aren't very large, the posterior doesn't change that much. So if you have a good approximation of the previous posterior, you can try to use it to kind of get a good approximation of the next one quickly. And by doing this, they weren't capturing the full posterior, just the center of mass of it, but at least they were avoiding a burn-in on the next chain, which made a big difference. In our case, well, we just shift all the particles that hopefully have reached a good approximation of the current posterior, and then we move them a little bit towards the next one. Right? You might want to do more than one step. That would also be reasonable. And the other thing I like about these algorithms is that they're relatively scalable. There's no accept reject steps, so you don't have kind of acceptance probabilities degenerating in one way or another, and that kind of helps sometimes in higher dimensions. The evaluation cost is not too large, so it's proportional to the number of steps that you take, then times the number of particles, times the evaluation cost of the gradients, which for many of these models is linear in the data, and the dimension of the data, latent variables and parameters. And if that's too large, you can use subsampling and replace. I mean, we haven't tried it just yet, but it's a fairly safe bet because we're basically doing something like SGD and EULA, and in those things you can replace gradients with stochastic estimates. And on top of that, the n factor here, you can kind of mitigate it by just vectorizing computations. So it makes that easy. There are some issues, some things we like less. So there's this ill conditioning that I mentioned before, which basically stems that for many of these models, theta gradients are much larger than x gradients. So you use the same step size to update both. You end up having to choose a small step size to stop the theta coordinates from diverging, but then you get very slow mixing on the x's. So you want to be a bit more careful about that. But there's kind of easy ways of doing that. And I can elaborate on this if anyone's interested. Aside from that, they're biased. As I mentioned, you only get stationary points. And there are restrictions on the type of problems you can deal with. Euclidean parameter and latent spaces and differentiable densities, and it's not hard to find models that don't satisfy these things. But it's also not too difficult potentially to tweak these methods of data. There's a little bit of an overwhelming amount of open directions here, and I think actually a fair amount that are worth checking out. I don't always get to say that. So if anyone's interested, please do get in touch. Just briefly, the theoretical analysis is wide open, and you can also maybe get good answers to things like how do you choose step sizes and that sort of stuff. So it's not just theory for the sake of it. And then there's many tweaks that you can do to improve these things. And the other day we're doing analogs of gradient descent, and gradient descent is not the state of the art in many optimization problems. Right? Things like people would use Adam a lot often. So maybe doing a momentum version of this type of thing, or choosing the step sizes in a smarter way. Right? Subsampling will also be pretty important to deal with big problems. You can probably do better approximations of the gradient flow, in particular replace Euler-Maruyama with something else. You can adapt things for remaining manifolds as long as you can still evaluate gradients. And more generally, instead of just tweaking these algorithms, I think it's also kind of fun to think of other optimization algorithms you can try to throw at this problem. So, things like Nesterov acceleration momentum, which I mentioned before, is kind of like an obvious choice because these things work well. You can try proximal stuff if you have non-differentiable densities, which are a thing in certain fields. And you can also just switch the geometry with respect to which you're defining gradients. We picked one that was easy to implement, but it's not necessarily the best one. I'm sure it's not. And then you can even think of other ways of trying to solve this problem, but updating theta and q together that are not like necessarily optimization methods. And we tried Metropolis Hastings tweak it somewhere in one of the appendices. And more generally, from where I started, I think there's other problems out there you can try approaches along these lines. Okay, so these are the references that I pointed throughout. There's a lot more inside the preprint. Thank you very much for your time and your attention. Are there any questions?